Okay, apologies from my end. I had actually um, joined the wrong link today, so I had started teaching over there, but then I soon realized that okay, I have to join some other link. Anyways, I think I'm going to record this session again, um, and today we'll be covering the contents of week three and week four. So yeah, let's begin. I hope my screen is visible and it's audible, although there's nobody to like respond to me, but um, I'm hoping that it's there. So, okay. Um, week three and four's contents. Okay. Majorly for uh, week three, uh, I'm going to begin with week three. Just a sec. Okay. Okay, so I'm going to begin with week three. Um, week three is basically discussing how we can consider the heat transfer mechanisms using simple resistance analogies. For example, um, let's say you have a let's say you have a plain wall here, and then there is another material wall here, and then there's like another material wall here. Okay, and all have the same area. Okay, um, all have same area. There's like different lengths, different lengths, and K, which is thermal conductivity. So, how are we going to determine the thermal conductivity of the whole system? That's possible by, so let's assume this is L1, this is L2, and this is L3, and this has, I'm going to say area, okay? So, this, let's say it has an area of A meter square. This is actually 3D. So, the frontal area is what I'm talking about. Okay, E- even the whole thing is like 3D like this. So basically, this area is A. So essentially, you can treat all these three. So let's say heat is going from this point to this point. Okay, temperature here is T1, temperature here is T2. Uh, it let's say falls like this. So you can essentially treat all these three as resistances, and heat is the one which is flowing. So it is like the current. So for the like for conduction, you essentially okay. We'll come back to the equation. Let's begin with the equation. Q equals K times A times delta T. Right now, that is our resistance. Uh, or we can say because it's particularly like current equals potential difference over the resistance, right? So here what is our current is our heat q. What is the potential difference? It is delta t. So what is resistance? It is delta t over q, right? So now from this, how do we get delta T over Q? Very simple, delta T over Q is L over K A, right? It's L over K A. So this is the resistance R conduction. Okay. Now, similarly, you can, like, for example, you can write the convection heat transfer equation as well. It is Q equals H A delta T. So what will be the resistance for convection? R convection is again, it is 1 over H A. H here is H convection. Although it's like very natural to, like, because we are not discussing uh, con- the radiation here. So H here is convection only. Now coming to radiation, the one which I have here is okay. So the radiation equation for Q equals uh, heat transfer is epsilon sigma A T raised to the power 4 minus T infinity raised to the power 4, right? Now, using this, if you try, so this is again like a big derivation, but if you try to bring it in a form that you want to calculate Q over Ts minus T infinity, uh, no, not this, essentially the reciprocal of this. So let me erase this part. So if you want to calculate the Ts minus T infinity over Q for this case, it will come out to be um, 1 over H radiation times A. And what is H radiation here? H radiation is epsilon sigma Ts square plus T infinity square and Ts plus T infinity. This is the one which I've got. I I don't remember exactly, but most likely this equation is correct. Please double check this, but I'm pretty sure this is correct. Okay, so H radiation is going to be this, and this is going to be our radiation. Okay, now there is something called contact resistance as well. So if we have two surfaces, this thing and this thing, okay, due to this contact here, there is going to be some resistance here as well. What is this resistance? Is called, let's call it RC. Okay, RC is delta T internal over Q dot over A. We will have more clarity on this if we discuss a problem, but I don't have the scope of discussing this in detail here. So I'll just put up the formula. Okay. What next? Okay. So we usually take three cases. One is the Cartesian coordinates, one is the cylindrical coordinates, and one is the spherical coordinates. So we just like right now here discuss the Cartesian coordinate system and how to calculate the resistances for the three cases. Let's say we have a cylindrical system. Okay. So cylindrical system. Um, so we have a cylinder and I'm sorry, my drawing is not good. Um, so let's call this as R1 and this as R2. Okay. And this has a height of, let's say, L. What is the uh, thermal, like conductive resistance of the cylinder? It is defined as R cylinder equals ln of R2 over R1 over 2 pi LK. Again, there is derivation of this one as well, but we are not going through it right now. If let's say we have a cylindrical system, sorry, spherical system now, spherical system. In one way, I think it's good that some of you watch recordings because you can go through this content in like 1.5x or like 2x even. So, okay. So, spherical system, let's say if it looks like this, okay. Cannot draw sphere in 2D plane. So, this is how it's going to look in the projection view. So, let's say again, this is R1, this is R2. So, R of sphere, and please note these are for conduction, okay. R of sphere comes out to be R2 minus R1 over 4 pi R1 R2 K. Yes. So these are two equations for the conductive resistances in the cylindrical and the spherical coordinates. What next do I have? Okay, critical radius. So there is something called critical radius of insulation. So actually, I was teaching this course the last sem as well, and what I'm looking at right now is the notes which I like the same lecture notes which I prepared last sem, so that I can cover the same concept. So it's like more convenient for me. So okay, let's say we have a wire, or let's say cylinder, okay, and it has some insulation. It has some insulation outside. Okay. So assume that like this inside is the copper wire. Okay. This is the copper wire, and outside this is like this part is the insulation. Oh, I have to like cover the complete area. Anyways, you guys understand. Okay. So this and this. Okay. Coming back to the pen. Okay. So this is insulation, and this is the wire. Ideally, I should have switched the colors because like wires are usually made of copper. But anyways, uh, so in this case, what is the Q dot? The heat transfer. It is so the temperature here is let's say T1, okay, and the temperature outside is T infinity. So Q dot is basically T1 minus T infinity over what do we have? Okay. R insulation plus R of convection. Because see, two things are happening. Here the temperature is T1, right? Now, from here there is one resistance up to this point. And let's say this temperature is Ts. And then there is another resistance here which leads to a temperature T infinity, right? So essentially we can say there are two resistances in series. And what are those? R of insulation and R of convection. What is R of insulation? This conduction, right? Conduction in a cylinder, you guys know the formula. It's ln of R2 over R1 over 2 pi Lk. And K here is K of the insulation, this yellow thing. What is R convection? Very simple, right? 1 over HA, if I'm not wrong. Yes. 1 over h times a. A is the area exposed. So basically, it is the circumference, which is 2 pi r times L. So we'll just write 1 over HA and H convection. Now, how do we get the critical insulation? First of all, why is there a critical insulation? Why are we talking about this concept? So, um, you see, if we go on increasing the insulation width, okay, insulation thickness, okay, if we go on increasing, and what is happening? Two things are going to happen. If we increase the insulation thickness, one is that uh, what will happen to our insulation? This thing. If we go on increasing R2 by increasing the insulation thickness, our insulation is going to increase as well, right? So this will increase. What will happen to our convection? This is A, so A is essentially um, 2 pi R2 times L. So R2 is going to increase, so our convection is going to decrease. So one of this is increasing, one of this is decreasing. So there is surely going to be some point at which Q dot is going to be maximum, not minimum. This is important. You'll have to think a bit to understand why I'm saying it's going to be maximum at some point in time and then it is going to die down. Okay. I mean, it's difficult to explain. It's somewhat like, um, I mean, essentially, what you have to do here is that you take um, dq dot over dr2 in this equation. You differentiate it with respect to r2 and make it zero. From that, you are going to whatever r2 value you get, that is the r2 critical. Okay, you can do the math at your homes. Right now, you don't have the time for that. So what comes out is that for a cylinder, the R critical is K over H convection, and for a sphere, it is 2K over H convection. How do we get to these? It's there in the book if you want to have a look. Not in your textbook because your textbook has uh, a limit to in how much detail they want to discuss. But the reference book from which I bring out the questions in Incropera, it has the like exact derivation as well as far as I remember. Most likely it's there. Okay. So essentially what happens is that the curve comes out to be like this. If there is like this is going to be Q versus R. Okay. R2, there is going to come a maximum point wherein there will be maximum heat transfer. So you can say point of minimum insulation, point of minimum insulation, right? Or we can say max heat transfer. So this is all what we had in week 3. Coming to week 4. Week 4, okay. Week 4 is essentially discussing the concept of fins. So, mm, let's say you had a surface like this and there was heat transfer happening. Okay, there was, it's heated, it has a temperature of Ts, and outside temperature is T infinity, and let's say Ts is greater than T infinity. So the surface is losing heat, right? Now, if you want the surface to lose heat quickly via convection, the convection equation is Q equals H A delta T, right? Where wherein delta T is Ts minus T infinity. Do you have a control over Ts? Okay. Do you have a control over Ts? No. Do you have a control over T infinity? No. Do you have a control over H? Actually, we don't. We don't because H is actually dependent on the medium which is there. So let's say whatever air here is present, its density, its temperature, depending on that, H is decided. Okay. And its speed as well. But what's in our hands and what's good is the area. So this is what people exploit. People actually try to use, if you increase area, then Q dot increases as well. Okay. So what they do, they make fins like this. So if you make a fin, now even the temperature here is Ts. The temperature here we will discuss later. It's called T tip of fin. Okay, I'm going to say T tip, and how the temperature varies all along this. This is what essentially we are going to discuss in this topic of fins in week 4. And okay, this is called T base. T base and T tip, essentially because we are trying to talk about the fin itself and not now worrying about the surface. So, what is the temperature distribution inside the fin? People are concerned about that. So, that is why we just look at the fin, we don't look at the surface. Okay. So, that is why this is called the base because this is attached to the surface. So, we say T base and this is T tip. Okay. And very naturally T base is going to be equal to Ts, and it's going to reduce slowly if Ts is greater than T infinity. So this is the concept of fins in like very very brief. Now, uh, now what is the like distribution of temperature inside the fin? Okay, inside the fin. It's so if you just what people do usually is that um, how they calculate. I'm not going to actually calculate and show you guys, but just in very short, if I can draw nicely. Hmm. Let's say this is the fin which we are talking about. This extended area, this thing, okay, this thing. So how do they actually end up calculating the distribution of temperature? They take a very small portion of this fin, okay. This is of, let's say, dx length and all over, okay. It's like dx is the thickness of this layer, and then they calculate how much heat transfer is taking place through this dx element and how much is its length, how much convection is taking place. Based on that, we are not discussing that. We could, but we don't have time. So uh, essentially the equation which finally comes out for distribution of temperature inside the fin is d square theta over dx square minus m square theta equals 0. If this is not making sense to you, it didn't even make sense to me while I was going through this the first time. So never mind. What is theta? Theta here is T minus T infinity. What is T? T is the temperature inside the fin. Which temperature? Okay, why are we actually doing this? We are actually wanting to calculate, let's say, let's see this in 2D, okay? What if I want, I'll ask you what is the temperature at this point in the fan. Here I know the temperature is TB or TS. Here I know it is like, okay, as of now I don't know, but okay, we'll discuss a few cases about this. What is the temperature here? This is what we are trying to calculate. So using this equation, we are actually able to do that. So what is T here? T is the temperature inside the fin at what position? At whatever position you are looking at. Okay. What is T infinity? T infinity you guys know. What is M? M is a constant. You can say M square is H P over KAC. I forgot what is P, but it will come up, I think, during the Q&A session, most likely. H is the convection heat transfer coefficient, K is the thermal conductivity, A is the area. Um, this actually, so if you have to solve this, uh, you integrate it twice and then you get theta as a function of x is c1 e to the power plus mx plus C2 e to the power minus mx. This is actually the general solution of such differential equations. Now we have to put the boundary conditions to finally solve for the temperatures, right? What I'm doing here is essentially completely discussing the derivation, but okay, we have time for that. Um, Now there can be a few cases, okay? What's happening at the fin tip? Now is when we are discussing this. Okay, fin tip. There can be multiple cases. One is that there is infinitely long fin. Okay. Second case is adiabatic fin tip. Okay. Third is, let's say there is a specific temperature at the end, at the tip. Okay. Let's call it T2. Okay. And then there can be a fourth case where it's fin. So in these cases we are going to assume that fin is actually not convecting, but in the fourth case we'll say fin tip is actually convecting heat as well. I'll explain all these four. Okay, so if let me choose the green color. If this is the fin, okay, this is the tip and this is the base. Okay, now let's say if we have a infinitely long fin, what's going to happen in this case? The outside temperature is T infinity, here the temperature is TB, here the temperature is T tip. Okay. If the fin is infinitely long, this TB is not going to affect the temperature of tip, right? Because it's very far away. So in the first case, we can say T tip is equal to T infinity. Hopefully I'm correct. Because I don't have this thing in my notes, but this is what I'm guessing most likely is true. What happens in the case of adiabatic fin tip? In the case of what is adiabatic? Adiabatic means there is no heat transfer which is taking place through the tip. So in that case, we can say that d theta x, because at tip the temperature is not. Why I'm saying theta? Theta is ts. Sorry, t minus t infinity. Let's erase this. Okay, so that is why if like I can say dt over dx as well, but we can also say d theta over dx because t infinity is a constant, so it's gonna like vanish to zero. Why I'm using theta? Because it's easier to use this equation for the boundary conditions because we essentially have the main equation as well in theta. Okay. What if there's a specific temperature at the tip? The boundary condition, which is there is T tip, very, very simple. Right? T tip is T2, not T infinity. And if fin tip is actually convecting the heat, in that case, if let's say in all these three cases, we assume that only the convection which is taking place is through this curved surface area of the cylinder. Okay. And tip, because it's very, very small, it's not convecting. Okay. But what if this also is convecting? What's going to happen in that case? It's very, very easy. Um, the whole area now becomes like, usually we used to take this as the area, right? This curved surface area. So if this were a cylinder, we would have taken area equals uh, 2 pi r times L, where L is the length of the fin and r is the radius, right? But and the tip is not convecting. So the heat transfer before, uh, if the tip is not convecting heat, then the heat transfer equation is Q equals H times what is A 2 pi r times L times delta T. What is delta T? That is again variable, but okay. Um, Now, if the tip also becomes convecting, then we can say Q equals H times 2 pi R L times delta T plus H times um, the area of the tip, which is pi R square times uh, um, T tip minus T infinity. This is because this is also convecting. This thing is also convecting, and this thing is also convecting. Okay, so what's the efficiency of fin? Okay, so efficiency of fin is q dot fin over q dot fin max. Uh, so what is q dot fin and what is q dot fin max? So if we have, let's say this is the fin which we've got, and this is the positive x direction, this is x equal to 0. The temperature curve usually is like this inside the fin. This is TB and this is T tip. Okay, it's you gradually falling down because TB is greater than T infinity. Then what is Q dot fin max? It is if the whole fin were maintained at T equals TB. You can see that the temperature as we move away from the main source, the temperature keeps on falling. So even the heat transfer rate keeps on falling because heat transfer rate is dependent on the temperature difference between the surface and the surrounding. And because the surface temperature is falling, so the difference is also going to fall, so the heat transfer is reducing. But if the temperature were TB, if the temperature curve were like this called Q dot fin max. This is the curve of Q dot fin max. This is a theoretical way of calculating the efficiency of fin. Because Q dot fin max is actually practically non-existent because the fin temperature is surely going to fall because it's going away from the surface. And what is Q dot fin? Q dot fin is the heat transfer rate along this green curve. I could have explained more, but again, we are short on time. So now another equation. This one was fin efficiency. Okay, fin efficiency. What is the second one? Second one is fin effectiveness. In fin effectiveness, we call it epsilon of fin. It is Q dot fin over what if the fin was not there? Okay, I think this is very, very simple. Um, like, what is the benefit which you're getting by adding the fin? If it's like too negligible, if the epsilon is very close to one, then the fin is non-effective. But if it's very it's very high, let's say two or three or something, usually it's between one and two, then your fin is like very good. And even the fin FE, okay, we'll talk about these things in questions. I think I have three questions for you guys today, and there is no one to respond back to me while I'm um, waiting for somebody to respond to me for the answers or something. So I'm just going to solve all three. You guys can pause the video and then try, and then go through the solution, whatever works for you. First question is, where do I have it? Hmm, okay. 3.57. Hmm. So it says, okay, 3.57. It says consider a 5-meter high, 8-meter long, and 0.22 meters thick wall whose representative cross section is as given in the figure. The thermal conductivity is also given. Um, okay. Then thermal conductivity of each of the contents A, B, C, D is given, and the left and right surface of the ball are maintained at uniform temperatures of 300 degrees Celsius and 100 degrees Celsius. Assuming heat transfer through the ball to be one-dimensional, determine the rate of heat transfer through the ball, the temperature at the point where the sections B, D, and E meet. B, D, and E, okay. And the temperature drop across the section F. Can I bring in the question here somehow? Let me see. Teams. Because that way it's going to be very, very convenient. Yes, I can. Capture and I'll paste it here. Okay, this is actually new to me. I used to do it previously, but I have forgotten. Insert from clipboard. picture. Anyways, I think I'll have to draw it again. Um, let me see. Okay, I think I'll figure it out later. As of now, I'm just going to draw it. Okay, so we have multiple walls here. Let's go to the drawing tab. This is A. This is C. Then there's. It's a very easy. Okay. This is C. This is also 4. This is also. And this is 8 meters. And this is B. This is C. This is D. This is E. And this is F. And this is 6 centimeters. And this one is centimeter as well. Happening. And let's see, this one is uh, 3. This is, this is, this is 6. This is not a very difficult problem, actually very easy problem. So I'm just going to solve it in like crux, and then we'll move on to the next problem. Where do I have the. And what is delta TF? What is the temperature drop across F? Hmm, okay. Now they have given, what else do we have? We have thermal conductivities of each of the material. We have it as Ka equals Kf equals 2, Kb equals 8, Kc equals 20, Kd is 15, and Ke is 35. Okay, what else do we have? I think that's it, right? So this very simple problem. First of all, you see the heat transfer. They're saying that heat transfer is happening in uh, 1D. Okay, so heat transfer is taking place only through this route. Okay, only like this. So few things are in series. You can see that. Okay, green pen, okay. This is a resistance, this is another resistance, this is another resistance, and this is another resistance. Now let's call it R1, R2, R3, R4. Okay, what is R1? R1 is very, very simple conduction resistance. It is in a Cartesian coordinate system. Conduction, what is R is, I think, L over Ka. This is R1. What is R2? R2, you can R2 is basically three things are in parallel: C, B, and C. So you can apply the parallel rule of resistances, in which you can say 1 over R2 is 1 over RC plus 1 over RB plus 1 over RC. Okay. I could have written 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but I think it's very, very obvious which C am I referring to when I'm saying RC, and which C is this one. This is, so this is the one in the first term. In the second term, this is the one which we are talking about. In the third term, this is the one which we are talking about. This is how we calculate R2. R2 is the um, R2 is the thermal conductivity of this part, this whole part. Okay. Now we have, similarly, let's calculate R3. R3 will be 1 over R3 is 1 over RD plus 1 over RE. Now this RC and this is A of A, or I could have written RA. And what is R4? R4 is essentially again a single block, so we can say R4 is RF. Now, what is RF? RF is L over Ka for F, right? Um, Now, using these four things, if you can calculate R1, R2, R3, and R4, let's say you have the values. Do I have it right now here? Let me check. I don't have the specific values, but I think I have the final answer. So you can say our total is, in series we have R1, R2, R3, and R4. So R1 plus R2 plus R3 plus R4, right? This is our total. And they're asking for Q dot. So Q dot total is delta T over R total, which is 300 minus 100 over R total. And if you please calculate, see, unless you guys solve the problems, you might understand everything, but unless you do it yourself, you won't be able to perform well in your examinations. uh, this I'm speaking from my own experience. So and even you guys might have experienced this is not the first semester of yours. So from this you will get Q dot as I don't have a point here. 191 times 10 to the power 5. What? It could be 1.91 as well, but what I have, I don't see the point here in my last year's notes. But there is a good possibility there's a, like, it's 1.91. So if you get 1.91, that's correct. But if you get 191 times 10 to the power 5, that is also correct. So choose accordingly. Okay. Next problem. Let's have it. Next problem says that repeat this problem assuming the thermal contact resistance at the interface of D, F, and EF is something. So it's again very simple. D and F. So we are saying there is some contact resistance here, and E and F. Okay, this one as well. So some resistance here as well. This is 0.00012 meter square. Okay, so I think I should do it here. Our contact is 0.00012 meter square times delta C over what? So again, very simple. Our contact as well. Okay. I mean, there's nothing to solve as well. Um, we'll have, do I have a final answer? Okay, I think I dropped off the two sub parts of the previous problem as well. But this is how you are going to solve this short thing, 3.58. I'll maybe give the final answer to this one, but let's complete the previous problems. 3.57, B part and C part. So in B part, they are asking what is the interface temperature at this point. The interface temperature here. How do we calculate it? It's very simple, right? Very simple. You see only from you see only this part. Okay. Try to see only this part. Can I erase it? Okay. Try to see only this part. I want a highlighter. Okay. Only focus on this tiny little part of the problem. Forget the rest. Uh, from here, you use the same heat equation. You use Again, q dot is equals to delta t over r. R is r3 plus r4. What is delta t? T interface minus 100 degrees Celsius, right? Because here the temperature is 100, here the temperature is T interface. The resistance in between is R3 and R4. So, and they are in series, that's why we write R3 plus R4. We know dot 191 times 10 to the power 5. So we have R3, we have R4, we have Q dot, we have 100. We can calculate T infinity. T interface, not T infinity. Or I'll write it here. So Q dot is equal to um, delta T over R. R is R is R3 plus R4. Delta T is T interface minus 100 degrees Celsius, and Q dot is 191 times 10 to the power 5. So we have R3, we have R4, we have Q dot, we have 100 degrees. We can easily calculate T interface as 263 degrees Celsius. This is what I have got. Most likely it should be correct. Actually, sometimes you might, usually this won't happen, but just to be very sure, this is just like a very short tip you guys can do. One is that see the temperature is 300 degrees Celsius. This is 300, this is 100 degrees Celsius. So the temperature should be somewhere